Hi everyone, so in this video I'm going to show you how to construct the velocity diagram for question 1 of your problem set. To do this you'll need a ruler, some set squares, pencil, sharpener, eraser, and of course your calculator. So let's start by reading the question. Crank OA rotates uniformly at 180 RPM in the clockwise direction. So if we look at the mechanism here, you have fixed point O, A is moving in this direction at 180 RPM. That's the only information you have for this diagram. And we're also given the lengths of all the links in the mechanism in millimeters. We need to construct the velocity diagram and find the velocity of point D. We also have a suggested scale and the starting point given to you. So our first step will be to convert 180 RPM into something that we can draw on the diagram. Let's convert to angular velocity of AO, which will be 2 pi times 180 on 60. And if you do this calculation, that is 18.85 radians per second. Now we can convert this to velocity because we know velocity is angular velocity times the radius. So this will be 18.85 multiplied by the radius. So that is the length of this link OA in meters. Convert your millimeters to meters. So 0.15, and then this velocity of point A will be 2.83 meters per second. So we have meters per second. Our last step is to apply the scale. Our final distance will be 2.83 times 4. This is the scale that's always going to be given to you in the question, and that's 11.32 centimeters. So this is the velocity or the location of point A. Let's go to our diagram and draw in that line. Velocity is perpendicular to the link because that's causing its movement. So our lines in this diagram are all going to be perpendicular to the links. OA, we have fixed point O. Now this technique that's used universally, this is where you combine all your fixed points into your starting point. So there are 2 fixed points in the diagram, point O and point P. They've been combined into this starting point. We have the link OA. Now A is rotating in the clockwise direction. So for this link to rotate clockwise around the fixed point O, our velocity is going to have to point downwards, because if our link is fixed and it's rotating down in the clockwise direction, the velocity has to be pointing this way. So our line in the diagram is pointing downwards. It's perpendicular to the link OA, and the length is 11.32 centimeters. To do a good perpendicular line, you put your ruler against the link as accurately as you can, and then I put my set square along the ruler. The set square passes through your starting point, I draw a line, and then I can go ahead and measure that to be my required length, and we're going to be as accurate as possible because this is a graphical method. So let me see here, 11.32, I'll make it a bit darker so we can see. That's the end of my point. That is point A. Don't forget to add your direction, again pointing downwards as I explained, and our label. So this is the velocity of A relative to O. That's our first point. Where do we go from there? Back to our mechanism, we can see that point A is connected to point B. So we have to go with the information that we have, which is point A, and now we try to find point B. So if we look for a new point, we need a relative equation. These are so important because they tell you what lines you need and how to construct your diagram. Velocity of B, this is our unknown, what we're looking for, equals velocity of A, which we know, we have point A, plus the relative velocity of B relative to A. So now I'm going to draw in two lines. I'm going to draw in velocity of B. Now this is relative to the fixed point, and I'm going to draw in B relative to A. And where those two lines cross, that is going to be where point B is. On our diagram, two lines. B relative to the fixed point P. So I'm lining my ruler along the link BP, putting my set square along the ruler. So this line is perpendicular to the link BP. Now I don't know the length of this line, so I'm going to draw it very lightly to start with until I know the length it should be. I don't know the direction either, I just know the location, and that is that it goes through the fixed point P and it's perpendicular to the link BP. My second line from my equation is B relative to A. So putting the ruler along the link BA, on the diagram I'm starting at point A. Remember, A is what we know, so I'm drawing my line perpendicular to the link BA. So where these two lines cross, this is going to be point B. So I'm going to now remove the excess lines that we don't need with my eraser. I'm going to go over these a little bit darker so we can see them. There we go, and this one too. Before we move on, I'm going to label my lines. So this line here is velocity B relative to the fixed point, and then I have velocity of B relative to A. B relative to A, my line points away from point A towards point B. And these labels correspond to my relative equation. All right, next point, back to our diagram. We have point A, we have point B. If we look at P, B, and C, they are on the same link. If they're on the same link, they have the same angular velocity. And we're going to use that to calculate the velocity of point C. How do we do that? Well, let's go through the equation together. So we have velocity of point C relative to P equals omega times the radius of CP, and velocity of BP equals omega times the radius of BP. If they're on the same link, the angular velocity will be the same. So let's rearrange these and say omega equals VCP on the radius of CP, and omega equals velocity BP on the radius of BP. I'm going to let these two terms equal each other. So velocity of CP on radius CP equals velocity of BP on radius BP. Velocity of CP is my unknown, so I'm going to leave that to one side. Velocity of CP equals velocity of BP times the radius of CP on BP. So now we have an equation we can solve. Velocity of BP, back to my diagram. I measure the length of the line BP, and my line is, let's see, about 5.9. 5.6, let's say it's 6. 6 centimeters, I'm leaving it as centimeters because I want my velocity value in centimeters. Then I need the ratio of the links CP and BP. So these are both given in the question. For CP, I need to add the two lines, this line plus this line, to get the total length of the link. So this will be 240 plus 210, so this will be 450 divided by the length of BP, which will be 240. Couple of points. 6 is centimeters because I want a value in centimeters for velocity of CP, so I can add it straight into my diagram. And I haven't bothered to convert the lengths of the links because it's a ratio, so these units cancel each other out. So if I do my calculation, I'm going to get divided by 240, 11.2 0.25. Now, because this is a graphical method, your values will be a little bit different, but you should get a value between 11 and 12, maybe 12.5 centimeters. So this is C relative to P, which means I have to start at the fixed starting point and measure from that line to get velocity of C. So I'm going to continue this down, and this will be there. So this is my point C. Now, adding in my direction and label before we move on to the next step. I'm running out of room on my page, so I'm getting another piece of paper to keep it neat. Looking at our mechanism here, we have A, B, C. The last point is point D. New point means a new equation. Velocity of D, this is our unknown, equals velocity of C, which we know, plus velocity of D relative to C. I'm going to draw in two lines, velocity of D and velocity of D relative to C, and that is where they intersect, that is going to be my point D. Now D is a slider, so instead of drawing a line perpendicular to the link, we can't do that with a slider, so our line is going to be parallel to the direction of motion, and the red dashed line is the direction of motion. So two lines. First line is going to go through the starting point and is parallel to the direction of motion of the slider. So it's important to still measure it from your diagram. Don't just eye this because it's not going to be exactly vertical. So how do we draw a good parallel line? Again, ruler along the direction of motion as accurately as you can. I put my set square perpendicular to the ruler, and then I can put another set square along the previous one, and this line is now going to be okay. So extend the line. I don't know the length, I only know the location, and that it is parallel to the direction of motion. My other line for this diagram is going to be on the link D relative to C. So D is a slider, but it still has relative velocity with respect to point C. If you're not sure how this mechanism is moving, have a look at the workshop slides for week 3, because this has the mechanism as a moving animation, and you'll be able to see how the slider and the other point fit together. So where they intersect, that is point D. I'm going to erase these extra lines. I'm going to make this dark so you can see it on the video. Now before I'm done, I need to label all my lines. So velocity of D relative to C, and then I have velocity of D relative to a fixed point or a reference point. So this is my completed diagram. The last part of the question was to find the velocity of slider D. So to find the velocity of any line, you take your ruler, line it up against your point of interest. So velocity of point D, I measure the length, so that's 9.4, and then you can convert that. So velocity of D, 9.4 divided by the scale, and then that will be about 2.4 meters per second. So that is my completed diagram for question 1. Remember, I have shown my full working, so I have my initial calculations, my relative equations. First one, I have a ratio calculation, my other relative equation, the completed diagram with arrows, labels, and points. I have my final calculations down the bottom. Okay, so in the next video we'll be constructing the acceleration diagram for this question.